In 11.1, we're going to be talking about similar polygons. Remember, polygons means many-sided figure. So similar shapes have the same shape, but not necessarily the same size. That's why they call them similar and not congruent. Two polygons are similar if all the corresponding angles are congruent and all the corresponding sides have the same ratio. So being similar has two parts to it. Part one is corresponding angles are congruent, and part two, corresponding sides have the same ratio. Make sure you know both of those. What do I mean by that? Even though all of the angles down below in the rectangle on the left have 90 degrees, they're not all similar. So look at the left, you see a rectangle. Look on the right, you see a rectangle. All the angles on the left are 90, all the angles on the right are 90. So all the angles are congruent, corresponding that is. And when you look at the sides though, the sides do not have the same ratio. What do I mean by that? Well, as I look at the left side of the first rectangle, 12, and I compare that to the left side of the second rectangle, 14, that ratio is not the same as the bottom of the left rectangle, 10, divided by the bottom of the right rectangle, 18. These ratios aren't the same. One is a 6:7 ratio, and the other one is a 5/9 ratio. So even though the angles match up, the side ratios do not match up, and so these two rectangles are not similar. Likewise, in the second grouping down below, what I notice is that the ratios do match. For example, the 12 on the left compared to the 15 on the left is the same as the 12 on the bottom compared to the 15 on the bottom, and so the sides are matching up just fine. However, when I look at the angle on the left here and the angle on the left here, 90 degrees and 120 are not congruent, therefore the corresponding angles don't equal each other and are not congruent, and these are not similar figures. So these are two non-examples of similar figures. These are not similar. Now when I look at this particular slide and I see these two trapezoids, what I notice is that when I start comparing sides, like the left side of the trapezoid to the left side of the trapezoid, that's a 9 to 18 comparison, or in other words, 1/2. I could likewise look at the top part of each trapezoid. Left is 10, 20 is right. Look at its ratio. That's the same as a 1/2. And I could do the bottom of these isosceles triangles, 8 and 16, and that's a 1/2. So we notice that all of the ratios, when we compare the two trapezoids, are the same. They all are 1/2. And then in addition to that, what I also notice is that I see the 45-degree angle top right matches up exactly, or in other words, is congruent with the top angle on the right. And then I also notice that the 135-degree angle on the bottom right is the same as the 135-degree angle on the bottom right. So what has happened here is that the corresponding angles are congruent, pink and pink, brown and brown, and the corresponding ratios are all the same as well, meaning looking from the left figure to the right figure, no matter where I look, the sides have the same ratio. That means that these two figures are indeed similar. Why? Because its corresponding angles were congruent and the corresponding sides had the same ratio. Looking at this information, we can use it to solve problems. So as I look down below at my two trapezoids down there, or sorry, not trapezoids, my two quadrilaterals, we can say that ABCD is similar to EFGH. And if we tell you that in the very beginning as a given piece of information, now what we can do is we can find X and we can find Y. So if I look for X first, and then y second, what I notice is that if I want to find my x value, I can set up a proportion. What do I mean by that? That means that I know that the ratio of 18 as it compares to 24, my first ratio, should be the exact same ratio as looking at the 21 compared to the x. And that's my second ratio. I set them equal to each other because I know that if these two figures are similar, that their sides have the same ratios. And that means we've set up a proportion, and a proportion is when two ratios are equal to each other. And now we have an equation with two fractions. I don't know if you recall this, but the way that we solve this is that we do something called cross multiply. So I'm going to take and multiply the 18 times the x, that's what I see on the left-hand side of my equation, and that needs to be equivalent to the 24 times the 21 on the right-hand side of my equation. When I multiply 24 by 21, I get 504, and then I divide both sides by 18, and my result is that I find out that my x turns out to be 28. So in the end, 28 is the answer for my x. The great news about finding y in this particular case is that I know that my y value, which is the bottom right angle here, matches up with the bottom right of the previous quadrilateral. And so I know that my y value has to be 83 degrees because the angles that correspond have to be congruent. In my last slide here, if we looked at similarity in coordinate geometry, we would see that we could multiply by a scale factor for each of the coordinates to transform it into a figure that's similar. So below here we have two parallelograms, and what you'll notice is that as we go from coordinates on the top left to coordinates on the top left, we have multiplied each coordinate by 2. And as we go from coordinates on the top right to coordinates on the top right, we have multiplied by 2. And funny enough, when you multiply 0 and 0 by 2, it doesn't change the coordinates, but it doesn't mean that we haven't multiplied by something, so we've also multiplied by 2 there as well. And then the last coordinates, 3, 0, if you double each of those, you will find 6, 0. So the scale factor going from the left figure to the right figure is 2. We have multiplied everything by 2.